Welcome to the deep dive. Today we're getting into something really fundamental for where AI is heading. Can AI actually, think? Not just churning out text or spotting pictures, but genuine reasoning. We've seen large language models do amazing things with language, right? But the real push now seems to be towards complex analytical thought. So our mission today is to sort of unpack what makes these reasoning models different, and crucially, how prompt engineering is like the key to unlocking what they can really do.
Exactly.
We'll touch on how these models try to shift from that quick, intuitive System 1 thinking towards the more deliberate System 2 processing needed for real problem solving.
And it's such a critical area because, well, real reasoning in AI, that's vital when you think about fields where mistakes have big consequences. Things like healthcare, finance, law. You need reliability there. And this whole effort, it's not just theoretical. It feels like a really pivotal step on that longer road towards artificial general intelligence, AGI. Just to set the stage, our conversation draws on the latest research, established guides on prompt engineering, trying to give you a solid picture of where things stand.
Okay, so let's unpack that. We all see LLMs generating fluent text, but what's the fundamental difference with these reasoning models? Are they just like smarter versions?
It's a bit more nuanced than just smarter. They're really optimized differently. Generic LLMs, they're masters of linguistic fluency, sure,
Right.
but they often stumble when you give them tasks needing deep analytical processing.
Right.
Reasoning models, though, they're specifically engineered for those kinds of challenges. Their main focus is on inference. What that means is they're tuned for logical deduction, complex math problems, figuring out cause and effect, even common sense reasoning. It's trying to go beyond simply matching patterns found in the training data. It's about deriving new insights.
So really getting them to deduce things, almost like a detective figures out a case.
Exactly like that.
Yep.
And to manage that, they often rely on multi-step processing. They're designed to handle problems that need a sequence of steps, right?
Yeah.
And crucially, maintain logical flow across that whole chain of thought. That's vital for complex stuff.
Makes sense.
A huge part of getting there is specialized training. We see advanced methods like reinforcement learning, RL. This basically rewards the model for successful problem solving, kind of like coaching it to reason better.
Ah, okay.
And it doesn't stop there. Post-training refinement is also super important for honing reasoning, improving factual accuracy, and ensuring alignment. We also see things like distillation used, to transfer these reasoning skills perhaps to smaller, faster models. Another angle is that System 1 versus System 2 analogy you mentioned.
Yeah.
Generic LLMs often seem to operate with that fast, intuitive System 1 kind of processing. Reasoning models, they're explicitly aiming for that slower, deliberate, analytical System 2 processing, the kind we use for tough problems. It's like shifting from gut feeling to careful thinking. There's even research suggesting some advanced models might integrate different data types, text, code, math, images in a more abstract way, maybe closer to how our brains pull information together. Because there's often a trade-off, performance trade-offs. These specialized models, they might be slower. They might need more computational power, sometimes called thinking tokens, because they're doing that heavier lifting, that deeper processing.
That's really fascinating. So when we talk specifics, what are some of the key models out there right now that are really pushing the envelope on reasoning? I bet people listening are curious.
Sure. Well, DeepSeek R1 is definitely one to watch. It's shown strong performance, especially in math and coding. And it's known for explicitly using that RL technique to boost reasoning.
Okay.
Beyond that, you hear a lot about OpenAI's more advanced models, the O series, like O1 and O3, Google's Gemini family, xAI's Grok, Anthropic's Claude models. They're all players seriously pushing reasoning capabilities forward. When people compare them, it usually comes down to their architecture, how they were trained, and importantly, how they score on reasoning benchmarks.
And stepping back a bit, what about the wider research scene? If someone wants to, really dig into the papers, where should they be looking?
Oh, platforms like ArtSift are just buzzing with this stuff constantly. You can find surveys that try to categorize all the different ways people are trying to enhance reasoning, new prompting techniques, changes to model architecture, different learning methods.
Right.
There are specific papers looking hard at things like post-training refinement, how chain of thought performs in really long context, or using external programs to help, like the PAL approach. Keeping up with that research really helps understand how to best work with these models.
Which leads us perfectly into prompt engineering. If these models have this latent reasoning power, how do we actually tap into it? That's where the prompting comes in, right?
Yeah, absolutely. It's all about the prompt. Unlocking what these models can do really hinges on how well we craft those prompts. And prompts here aren't just simple questions. They act as detailed instructions. They provide the necessary background. They set the rules. They guide the model. For complex reasoning, getting the core components of that prompt right is just essential.
Okay, so walk us through that. If I want a model to perform some serious deduction, what absolutely needs to be in my prompt?
Okay, first off, instructions. You have to be crystal clear about the task. And importantly, the kind of reasoning you need. Is it deduce the conclusion, solve this step by step, analyze the causes, compare these arguments logically?
So no vagueness.
Exactly. Vague instructions will lead it astray, almost guaranteed. Second, information or context. This is critical. You must provide all the background info, the data, the rules, constraints, premises, whatever the model needs to work with. If it's missing key context, the reasoning just won't work. You mentioned DeepSeek R1 for coding. It needs the precise problem setup. Or think about the PRISM framework. Problem, relevant info, success measures. It really hammers home providing that info up front.
Makes sense. What about examples? I keep hearing few-shot learning is a big deal.
It is. Examples or few-shot learning can be incredibly effective. Showing the model the kind of reasoning steps you want through examples. That boosts performance significantly, especially for patterns like chain of thought we'll get into. You're basically teaching it how to think for your specific task.
Showing, not just telling.
Precisely. And finally, don't forget the output format. Tell the model exactly how you want the answer presented. Should it show its work in a numbered list? Give the final answer, then the steps. Put the result in a table. Specifying this makes the output structured easier to understand, easier to check.
Okay, so nail down instructions, context, examples, format. Got it. Then you get into the specific patterns of prompting, the techniques themselves. Which ones are really making a difference for complex reasoning?
Right. There are several powerful patterns, but let's highlight a few key ones. The chain of thought pattern, or COT, is probably the most famous right now. It's fundamentally about encouraging the model to think step by step. You often trigger it with simple phrases like, well, think step by step, or by giving few-shot examples that lay out the intermediate steps. COT is super useful for arithmetic, logical deduction, anything requiring multiple stages. It makes the reasoning explicit so you can see it and hopefully verify it. It helps reduce errors.
Can you give a quick example of COT in action, maybe with a logic puzzle?
Sure, yeah. Let's take a classic. You have suspects A, B, and C. A says B did it, B says C did it, C says I didn't do it. Only one person is telling the truth. Who did it? Think step by step. Using COT, the model would ideally walk through scenarios. Assume A is truthful, then B did it. Does B's statement, C did it, become false? Yes. Does C's statement, I didn't do it, become false? Yes. Contradiction. It tests each possibility systematically.
Ah, I see. You can follow its logic.
Exactly. Another really practical pattern is tool use integration. Think frameworks like PAL or React. Here, you prompt the model to use external tools. Calculators, maybe execute some code, call an API, generate code to help itself reason.
Okay, so it offloads some tasks?
Precisely. Gets around inherent LLM limitations, like doing precise math or getting real-time data. For instance, models like OR LLM agent use this to automate solving operations research problems. If you ask, what's 15.7% of $3,456.78? Write and execute Python code, the model uses the code for accuracy, rather than trying the math itself and maybe messing it up.
That sounds incredibly useful for reliable results. What other patterns are commonly used?
Well, there's the role-based pattern. You tell the model to act like someone specific, acting as an experienced financial analyst.
Yeah.
This primes it to use the right kind of vocabulary, the right kind of reasoning methods for that role.
Got it.
And the self-consistency pattern. This is interesting. You get the model to generate multiple different reasoning paths for the same problem, and then you pick the answer that shows up most frequently. It adds robustness, especially for math, or maybe ambiguous questions where there isn't one single clear path.
And the research keeps pushing, right? I'm hearing about even more complex ideas, things like graph of thoughts.
Yes, absolutely. The innovation is nonstop. We're seeing advanced techniques emerge, like algorithm of thoughts, AOT, which tries to embed algorithmic search patterns, like a tree search, directly into the prompt structure to explore solutions more systematically. And graph of thoughts, GOT, as you mentioned, it models reasoning more like an interconnected graph, allowing for more complex ways to combine and refine different lines of thought. For models trained with reinforcement learning, the prompts often need careful alignment with whatever strategies the model learned during training. And then there's self-correction or reflection, prompting the model to actually critique its own work. Review your steps. Are there any errors? Could there be alternatives?
Okay, this all sounds incredibly powerful, but I imagine it's not perfect. Can't be easy. What are the really big challenges still facing us in getting models to reason reliably?
Oh, the challenges are definitely significant. A huge one is simply evaluation. How do you really assess if the steps in the reasoning are sound, not just whether the final answer happens to be right? That's hard.
Right, the process matters.
Then there's the ever-present issue of hallucinations. Models can generate steps that sound plausible but are just wrong. Or they generate incorrect facts. Logical consistency is another major hurdle. Can the model stay coherent over a really long, complex chain of reasoning? Often they struggle. We also see generalization gaps. They might be great on problems similar to their training data, but fall down on truly novel ones. And even with bigger context windows, memory limitations can still be an issue for tracking all the necessary information through very extended reasoning processes.
So quite a list. What's the path forward then? Where's the research focused on tackling these issues?
Well, the field is moving incredibly fast.
Yeah.
We're constantly seeing improved models coming out with better inherent reasoning abilities built in. There's a lot of work on hybrid approaches, maybe combining LLMs more effectively with older symbolic AI techniques or knowledge graphs or better external tools. Scalability and efficiency are also big drivers. How can we make this deep reasoning less computationally expensive? And one really promising area is process supervision. Instead of just training on the final answer, you train the model based on the quality of its reasoning steps. That could be a game changer for ensuring logical soundness.
Okay, so wrapping this up, what's the main takeaway for you, listening in? It seems mastering prompt engineering for these reasoning models really demands understanding two things, doesn't it? You need to get a handle on what these advanced models can do, their capabilities, but just as importantly, you need to know the specific techniques, the patterns that actually draw out and guide that reasoning. Hopefully, you now have a much clearer picture of how AI is moving beyond just talking fluently towards actual reasoning, and you've got some insight into the practical tools and patterns needed to work with it.
And maybe a final thought to leave you with. As these capabilities keep getting better and better, and we face these challenges we've discussed, how might that line between what we call sophisticated pattern matching and what we consider genuine reasoning actually shift? What does it mean if that line blurs? Especially as AI takes on more critical decision-making roles, it's certainly something to keep thinking about in this incredibly fast-moving field.